Hello, my name is Daniel Nenny, and I'm the founder of SemiWiki.com, the open forum for semiconductor professionals. Since going online in 2011, SemiWiki.com has experienced more than 3 million users. If you're not a SemiWiki member, please register as my guest. I hope to see you there. Today's webinar is titled Chip-to-Chip Communication for Enterprise and Cloud in partnership with SiFive. Presenting is Keaton Mehta, Director, SoC IP Product Marketing at SiFive. Keaton is responsible for Interlaken, Ethernet, HBM, and other high-speed interfaces. Also presenting is Sandeep Gupta, Senior Director, SoC IP Engineering at SiFive. Sandeep leads the company's IP engineering effort and manages the entire soft IP portfolio. After the presentation, there will be a question and answer session, so you definitely want to stay for that. All right, let's get started. Over to you, Keaton.
Thank you, Dan. Hi, everyone. Thanks for joining the webinar today. I will be talking about some of the key applications and why Interlaken is protocol of choice for these data-intensive applications. The applications that we are looking at are enterprise networking, AI, machine learning, data center, high-performance computing, and cloud. There is one common theme between all these applications, and that is more and more data. Now, when we implement an ASIC and SoC for this kind of applications, it requires more data traffic going in and out of your SoC, which further requires a high-speed interfaces. This is where Interlaken comes into play. I like to reference one of the quote from Gordon Moore at Intel that is dated all the way back in 1965. He says, it may prove to be more economical, build large system out of smaller functions, which are separately packaged and interconnected. Interlaken just allows that kind of package interconnection. In fact, disaggregation is a new trend. More CPUs, more chips, and more dies all connected to each other. This is where the chip-to-chip connectivity comes into play. If you're aware of the SoCs that are getting larger and larger today, hitting the reticle limits, the problem it brings is lower yield, higher power, increased cost per die. The lower yield because as the reticle sizes gives you a bigger die, the yield of that particular die goes down. The diagram here shows how two packages are connected using Interlaken and PHY. I mentioned PHY because Interlaken is actually agnostic to physical layer. It can be high-speed SerDes up to 112 gig, or it can be bunch of wires connected in parallel. A whole new topic on die-to-die that we will address at some future seminar. In one of the engineering paper at Facebook, they mentioned how they build server racks. It says, instead of large devices and clusters, we disaggregated the network into small identical units called server pods and created a uniform, scalable, high-performance connectivity between all the ports in the data center. The connectivity is where we foresee the Interlaken is coming to play more and more. Coming back to AI and machine learning, there are so many use cases where clusters of compute and or CPU elements are used to process the data in parallel. All this data that has been processed needs to go to the adjoining chips without any latency, as fast as possible, and with highest throughput. Now, as we hit the reticle limits, that data needs to go and connect to the other chip. Once again, Interlaken is protocol of choice here. The diagram on the bottom just shows that, how processing of all the reticle data connects to the next chip. Interlaken has some unique advantages compared to the heavyweight protocols such as Ethernet and PCIe. Heavy in terms of the gates and complexity. Interlaken is truly a lightweight protocol. First of all, it is a narrow interface requiring very few IOs. As I mentioned earlier, it is to some extent physical layer agnostic. It can use 112 gig SerDes, or it can go over parallel wires at a lower speed with the clock forwarding. Interlaken provides flow control and quality of service through almost 64,000 virtual channels. It is scalable up to 48 physical channels, so you can literally connect 48 chips together. Finally, the low protocol overhead offers a very small footprint core with a modular design, allowing customer a true configuration play on the latency and the functions. If all these features are not enough, I want to highlight that OpenSilicon, a SiFive subsidiary, was a founding member of Interlaken Alliance. We have over 75 licensees today and silicon proven with the tier 1 customers. So we are now introducing a low latency Interlaken variant of our very successful Interlaken IP with a high throughput. This IP will fit very well into the applications we talked about earlier, and also the NIC accelerators, NAND flash controllers, and the list just goes on. In fact, some of our customers are asking for end-to-end latency in the range of 20 to 40 cycles between the two chips. This is very much possible depending upon the customer configurations for connectivity. If you need more information, please take a look at the product brief on our Interlaken webpage. Now we want to take some real-life examples. Here, we want to show how extensively Interlaken is used in server and line cards. On the left is a typical data center chassis with a bunch of line cards and backplane connecting to switch and fabric cards. On the right, we have zoomed in to one of the line cards. As you can see, Interlaken has found its place connecting NPUs, traffic managers, switch fabric units, all of them requiring high throughput. Interlaken provides high throughput for all these connections. Below there are a bunch of other applications that can be used in enterprise networking. Here is one more use case of Interlaken in a high performance computing. You can see here that each node on a particular board, let's call it a compute element, and they are connected either among themselves or to the control element C1 or C2. The control elements are further connected to other boards either in the north-south direction or east-west direction. This kind of connection provides a true scalability for high-performance computing. Most of the links here we foresee are going to be connected using Interlaken, a truly scalable architecture that easily allows more nodes to be added or subtracted. Finally, I like to highlight our Interlaken IP portfolio. We have Interlaken up to 1.0 terabit per second available today, including the Interlaken look-aside functionality. We also offer a forward error correction modules that customer can opt for a 56 gig PAM4 based SerDes or higher. We just introduced Interlaken-Low Latency for AI and high performance computing application. Interlaken up to 2 terabit per second is also on our roadmap. With that said, let me invite my colleague Sandeep. He will go through some of the important features of Interlaken and explain how latency Interlaken works. Thank you. Pass it over to Sandeep.
Thank you, Ketan. So I'll go into a little bit more details about the SiFive Interlaken core that we offer. So I'll just start with the standards. So the Interlaken standards is maintained and promoted by the Interlaken Alliance, of which SiFive is a founding member. The Interlaken Alliance has various specifications as listed here. That is the Interlaken protocol definition, look-aside protocol definition, retransmit extension, dual calendar extension, interrupt recommendations. And we support all of these standards in our core. Now, the SiFive Interlaken IP is available in two broad flavors. The high bandwidth version, which can go up to 1.2 terabits per second, and the low latency version, which reduces the latency up to 50% as compared to the high bandwidth version. So now we'll look at some of the key features of the high bandwidth Interlaken IP. It supports up to 1.2 terabits of bandwidth, and it supports 48 SerDes lanes with custom width support. The SerDes rates supported are from 3.125 Gbps to 56 G PAM4. We also support the KP4 FEC. The user interface, which is the custom user interface, supports various configurations of 128-bit and 256 bits, which is 1x 128-bit, 2x, and 4x 128-bit. Similarly, for 256 bits, we support 1x, 2x, 4x, and 8x configurations. We support up to 256, which are extendable up to 64K logical channels. We have lane resiliency support with independent lane enable and disable feature, lane bifurcation support, Interlaken retransmit extension support, Interlaken look-aside protocol support. We support simultaneous in-band and out-of-band flow control with programmable dual calendar, built-in error detection and injection capability for testability. Now let's look at the block diagram. In this segment, we will talk about the single segment configuration. But before that, let me briefly explain the block diagram of the SiFive Interlaken core. As shown, there are four major blocks. The user interface, which includes the optional retransmit feature. This block essentially takes the user data through a custom-defined user interface. This interface can be configured as shown here in this top corner. Next comes the frame formatter and the flow control block, which takes the user data and converts it to a metaframe word, which will be placed in each individual lane. The output of the frame formatter block is referred to as pipe. The lane distribution block then takes the 64-bit pipe data and converts it to lane data. Finally, the lane remapping block maps the logical lane data to physical lanes. The Rx path is exactly the reverse function of this and goes to the complementary blocks in the received direction. Now in this figure, you can see we have a single user segment of either 128 or 256-bit wide. With 128-bit interface, we can support up to 100G throughput, and with 256, we can support up to 150G throughput. The number of segments, pipes, and lanes are user configurable depending upon the bandwidth requirements. Now let's look at the two-segment user interface. With two segments, we can support up to 300 Gbps for 256-bit interface and 200 Gbps for 128-bit interface. Now, even though the number of segments are double, the IP core is still backwards compatible. That is, it can support the single segment mode, which basically means that you can support 100G or 150G throughput. Now, because we are increasing the number of segments, the overall processing power of the IP also needs to increase. This implies that the number of pipes and lanes will also double. Similarly, for higher bandwidth requirement, the number of segments can be scaled up to a max of 4x 128 or up to 8x 256 to support up to 1.2 terabit throughput. In all these options, the individual segments, pipes, or lanes can be enabled or disabled to support a lower throughput to reduce the power when the chip has lower bandwidth requirement. The max number of lanes supported are 48. So for a 1.2T throughput, you can configure 48 lanes of 25 gig NRZ SerDes or 24 lanes of 56G PAM4 SerDes. Now here we will look at the remapping concept. But first, let's understand the difference between logical and physical lanes. The lanes to the right of the lane remapping module are the physical lanes which connect to the actual physical SerDes. The lanes to the left of the lane remapping module are the logical lanes. As we have seen earlier, the frame formatter module takes the user data and strips it into 64-bit pipe data, and the lane distribution maps this to a logical lane which represents the actual lane to which it needs to transmit the data on logically. Now in the lane remapping module, these logical lanes can be remapped or connected to any of the actual physical or SerDes lanes. Now this figure over here shows an example of the lane remapping. This remapping can be done at runtime, that is during the IP initialization phase post-reset. This provides the user with two distinct advantages. It eases out the routing on the actual die itself, so you do not have to constrain the logical lane 0 to be placed close to the physical SerDes 0. Similarly, it eases out the routing on the PCB between the two chips. The second advantage is what we call as the lane resiliency feature, which helps in increasing the die yield. So for example, you need 24 physical lanes, but you can decide to add an extra redundant SerDes lane. In case of a manufacturing defect on any one of the SerDes lanes, you can remap any of the logical lanes to this redundant lane. So far, what we have seen are all different features considering a single core. Now let's get introduced to the concept of a multi-core IP. In a single core configuration, all the data from the user interface gets distributed and mapped to all the SerDes lanes connected or mapped to that user interface. So now you can basically connect one chip which supports say 600G using 24 lanes of 25G each to only one other chip with the exact same configuration. However, now consider that you have two use cases for a single chip, where in the first case, you want to take a 600G connection and break it up into two 300G connections and connect to two different chips of 300G each. So how we support is by bringing in the multi-core concept. In the multi-core IP, the first two blocks, that is the user interface and the frame formatter, are replicated twice. The user interface with the frame formatter constitute what we call as a single core. However, lane distribution and the lane remapping are still the same as in single core configuration and shared across the two cores. Now, depending upon the configuration at reset, you can enable a single core only, thus making this IP behave like a single core 600G IP, or enable both cores and create two data paths of 300G each. The important point to note over here is that the PCS and the FEC functionality are part of the lane distribution block. So this achieves a significant area when running the IP in the dual core mode, because the FEC and the PCS are now shared across the two cores. They still support a throughput of 600G. Similarly, the IP can be configured in a quad core mode. The slide here nicely summarizes the different configurations of a quad core IP and how they can be used with the exact same drop. So as you can see over here, we have three instances of this IP on three different chips. And the first two chips are connected using a single link of 1.2 terabits. And the second instance over here breaks up this 1.2 terabits into two pipes of 600 gig each. And similarly, the third Interlaken IP is breaking up the two 600 gig links into four 300 gig links. This feature is also what we call as the lane bifurcation feature. So far, what we have seen are the features of the high bandwidth Interlaken core. Now let's look at the low latency IP version of this Interlaken core. In this IP configuration, we reduce the latency up to 50% as compared to the high bandwidth. Now, for certain applications, the latency requirement trumps the bandwidth requirement. And usually these applications do not require such high throughput of 1.2 terabit. So for such applications, this low latency version is extremely useful. In this configuration, we are able to achieve significant savings in latency. However, the max bandwidth supported is 256 gig and a max of 8 SerDes lanes with a rate of up to 32 gig max. Now, because we are supporting only a max SerDes rate of 32 gigs, FEC support is also not required. The number of logical channels is unchanged as compared to the high bandwidth version. Similarly, all other features are supported like lane residency, lane bifurcation, retransmit, and look aside. And of course, in-band flow control and out-of-band flow control, along with error injection and detection capabilities, are supported in this version of the IP as well. Now, I would like to concentrate on how we achieve a lower latency in this IP. There are multiple factors, but I'll just focus on a few big items. The main feature that helps us reduce the latency is the retransmit feature and how we implement it. In the legacy mode, now this is the legacy mode of legacy implementation of the retransmit feature. Now, when a data comes in on the receive interface, the data goes and sits in the retransmit buffer until the entire burst is received. When this burst is received, at the end, we do a CRC24 calculation and check. And if it passes that check, then the data is presented on the RX user interface. So as you can imagine, because the data is stored in this buffer, there is an incurred latency, there is an inherent latency in the way this design is implemented. Now, if a particular burst does not pass the CRC check, that burst is just not passed forward onto the RX user interface, and it is dropped within the RX buffer, and retransmit request is raised. Now, unless and until we receive this errored burst again, all the subsequent bursts are dropped. Now let's look at what we call as the cut-through implementation of the retransmit. Now, as you can see, the retransmit buffer is eliminated, and all the incoming bursts are directly passed to the RX user interface. In parallel, the CRC24 check is performed. If a particular burst is an error, then a burst ignore signal is asserted on the RX user interface. Now, similar to the legacy implementation, from this point on, all the subsequent bursts are dropped from going to the RX interface until the errored burst is received again. So this is how we achieve a lower latency in the low latency version of the IP. There are additional factors like the no FEC support, and similarly, because of lower throughput requirement, the overall clock frequency of the IP is lower, and thus the number of flop stages also goes down. Now, in the end, I'll just talk about the deliverables that come along with the IP. The IP configuration is defined by the project control document or the PCD file, which is filled in by the customer. This is essentially the hardware configuration where the customer can specify the total bandwidth requirement, number of segments, lanes, pipes, whatever other features that we've already talked about, what support is required and what support is not required. Based on this PCD, we will generate the IP core, and then we will deliver that core. Along with the core, what you get is the Interlaken IP specification, of course, the product brief, the memory map register manual, the design and verification plan, synthesis scripts and static timing scripts, assertions for the user interface and config registers, and the test simulation environment. So that's it from my end. Back to you, Dan.
Well, excellent presentation. Thank you very much, Sandeep. Ketan, we have some questions. The first question is, why is there a high demand for Interlaken IP currently in the market today?
Yeah, that's a good question. Actually, the market is right now integrating more and more functionality in its SoC, and the SoCs are getting bigger and bigger. That's hitting the reticle size of what you can carve out of the wafer, which has a further penalty on the area, the power, and the yield of the die. So what is happening is they are trying to disaggregate those chips, and connectivity between those chips is where Interlaken is coming into play.
Okay, we have another question for you. Why does cloud, enterprise, and HPC prefer Interlaken IP for chip-to-chip connectivity, and what are the major advantages in these applications?
Yes, as I covered in my presentation, I think the major drivers are the latency and the performance, and Interlaken provides both of them. Nowadays, with the latency improvement, Interlaken has found its unique spot into this cloud and enterprise market, where the latency is very important, passing the data from one chip to the other one.
Okay, final question for you. What lies ahead in the SiFive's Interlaken IP roadmap?
Yeah, it is actually twofold. We are looking at it from the performance perspective as well as the latency perspective. Performance, we can keep increasing the throughput that Interlaken provides. 2 terabit per second is what we are thinking, which will help connect all these data-intensive applications. But also the latency, which is coming into play. What we are trying to do is optimize some of the modules in the Interlaken, particularly the forward error correction, because as the SerDes speeds are advancing onto PAM4-based architecture, it is going to be needing those forward error correction blocks. And we're trying to focus on some of the modules which can improve the latency. So it's driven based on latency and performance. That's where we are.
Excellent, excellent. Okay, the next questions go to Sandeep. Sandeep, currently the bandwidth supported by Interlaken-Low Latency IP is 256 gigabytes per second. In the future, will there be an increase in bandwidth, and will the number of lanes and lane bandwidth be increased?
Well, Yeah, so as I've mentioned in my presentation, yes, that is possible, and we can definitely do that. Even in the current configurable IP that we have, we can merge and increase the number of lanes. However, the moment we increase the number of lanes, the latency advantage is going to reduce. And as I've said, these are two very different use cases, the low latency versus higher bandwidth. And hence it actually does not make sense to do that. But if there is a specific use case, we can certainly do that.
Okay. Another question, for user interface options, will SiFive support 128 and 256-bit for Interlaken-Low Latency IP?
Yeah, so I think this is kind of similar to the previous question. So even though we can support it, it will not make as much sense because for higher bandwidth, higher latency comes into the picture, and we would need additional pipe stages to meet the timing. So the moment you increase the bandwidth, the latency advantages will continue reducing.
Okay. For the lane mapping feature, does the lane remapping for either of the two chips connected to each other map the lanes in an identical way?
Yes, they have to be because Interlaken as a protocol is a very light protocol, and it does not have lane identification on the data that is passed across the lanes, something similar to what Ethernet has. So the way you do the lane remapping on one end of the Interlaken, it has to be a mirror image on the other end. Otherwise, it won't work because that information is not passed across the link.
Okay, and we have time for one final question. If cut-through retransmit has lower latency, why is that not supported in the high bandwidth version?
Well, that's a good question. It can be supported. It's not that it cannot be supported, and we can achieve a lower bandwidth in the lower latency in the high bandwidth version of the IP. However, the issue is that the applications or the use cases which require higher bandwidth, they generally cannot tolerate errored bursts. So the moment we pass an errored burst, there's a lot of processing that needs to be done at the higher layers, which requires additional gate count, additional latency at their end. So these use cases prefer that we pass only good bursts to the higher layers, and hence there is that differentiation.
Very interesting. Okay, that is all the time we have for today. Thank you all for participating in the SemiWiki webinar series, and have a good day.